Okay, this is exam 2 for Physics 102, Spring 2014. Let's start with this circuit. What is the equivalent capacitance of this circuit? Okay, well first, I want to find the equivalent capacitance of these two that are in parallel. That's just going to be 1 plus 1 is equal to 2 microfarads. And then that leaves me with a 12-volt battery with a two 2 microfarad capacitors in series. And the equivalent of those is going to be 1 over 2 plus 1 over 2. That's 1 over 1, which is 1 microfarad. So C is number 1. For the circuit in the previous problem, what is the voltage across C3? Well, that's going to be the voltage across this capacitor. All right, and recognize that these two capacitors are the equivalent of this capacitor. And the voltage across this capacitor is 6 volts because I have two identical capacitors hooked up to a 12-volt battery, and so their voltage has to equal 6 volts, and it has to add up to equal 12 volts, and they have to be identical. So I have to have 6 volts each. And capacitors in parallel have the same voltage, so both of these capacitors both have 6 volts. So the answer to number 2 is 6 volts, which is C. And then number 3, what is the charge on C1? Well, C1 is this capacitor right here, which has 6 volts on it. And then my charge is going to be C times V. That's 2 microfarads times 6 volts. Or excuse me, 2 microfarads times 6 volts. That's going to be 12 microcoulombs. So B is number 3. A farad is the same as what? Well, I know that C is Q over V. Right, and C is measured in farads, so that's going to be Q in units of coulombs, V in units of volts. So coulombs per volt, that is D for number 4. Each plate of capacitor stores a charge of a magnitude of 1 millicoulomb. When a 100-volt potential difference is applied, the capacitance is what? So first of all, just want to recognize that when I have a capacitance, I have plus 1 millicoulombs, and then I have negative 1 millicoulomb. But when we talk about the charge on a capacitor, we just say it's 1 millicoulomb. So that's what it means by each plate. Now, here, I want to know the capacitance. It's Q over V. That's 1 times 10 to the minus 3 coulombs divided by 100 volts, or, 0.001 over 100. That's in, so that's going to be 0.00001 farads. And let's say we need to convert it to microfarads, so we need to move it over 6 spots. 1, 2, 3, 4, 5, 6. So it's going to be 10 microfarads. So B is number 5. The plate area and plate separations of 5 parallel plate capacitors are given. Rank them in order from least to greatest. So let's see. Remember, our capacitance is epsilon naught A over D. So we just want to take these and figure out how the capacitances are relative to one another. So let's start with the first one is just A over D. The second one is 2A over 2D, which is equivalent to A over D because those cancel. The next one is 2A over D over 2, which is equivalent to 4A over D. The fourth one is A over 2 over 2D, which is equivalent to A over 4D. And then the last one is A over D over 2, which is 2A over D. All right, these two identical, 1 and 2 tie, so we can get rid of some options here. That one goes away, that one goes away, and that one goes away. Only A and C list 1 and 2 as tying. And let's say we want to list them from least to greatest. So which of these has the least capacitance? Looks like number 4, A over 4D, has the least capacitance. So 4, let's just double check that. 4 and then 1 and 2 are bigger than that, and then 5 is bigger than that, and then this is the biggest of all. So yeah, so that's going to be A is the correct answer for number, what was that, number 6. Two identical capacitors are connected in series, and each identical to the first connected in parallel. The equivalent capacitance of the series connection is what? The equivalent capacitance of the parallel connection. So for the series connection, it's going to be 1 over C plus 1 over C. It's going to be 1 over 1, 2 over C, which is C over 2. And then for the parallel capacitance, it's going to be C equals C plus C, the equivalent, which is 2C. All right, so the equivalent capacitance of the series connection, which is this one, is 1/4 the equivalent capacitance of the parallel connection. Right? 20 microfarad capacitor is charged 200 volts. The stored energy is what? All right, energy is 1/2 CV squared. C is 20 times 10 to the minus 6. V squared is 200 squared. I think that's 0.4. 0.4 joules. So C is number 8. Consider the circuit. What is the charge on C2? Well, sort of drew it funky here, but this is the same as that. If I just draw C2 parallel in that way, you can tell that because if you follow along in the circuit, notice here I come into a break, and then I come into another break up here. Well, if I were to draw that, it would look like this. Where this junction is this junction right here, and then I would have another break up here, like that. All right, so that's what that circuit would look like. But if you notice, like even if I just find the equivalent capacitance here, 1, 2, and 3, if I treated them as separate parallel branches, I would add these up to equal 3, and then I would add that up to equal 6. Or I could just say 1 plus 2 plus 3, and then that would give me my equivalent capacitance, which would be the same. These circuits are the same. That circuit and this circuit are identical. Those are the same circuits. And so because it's in parallel, they all have the same voltage. And I'm looking for C2, so it has a voltage of 12 volts. And so it has a charge of 24 microcoulombs. That comes from Q equals CV. That's going to be 2 microfarads times 12 volts, which is 24 microcoulombs. That's a little tricky, but it's a common way to draw circuits. We'll see that again with capacitors. What is the equivalent capacitance of these capacitors? Okay, well, 3, 3, and 3 in series, that's going to be 1 over 1 over 3 plus 1 over 3 plus 1 over 3. That's 1 over 1. It's 1 microfarad for number 10. What's the equivalent capacitance of these capacitors? Well, in parallel, it's just 3 plus 3 plus 3. So that's 9 microfarads. So number 11 is A. Parallel plate capacitor initially has potential difference of 200 volts and is then disconnected from the charging battery. If the area of the plates is now doubled, what is the value of the voltage? All right, so it's disconnected from the charging battery. That means it has a constant Q. So Q is equal to CV, and Q remains constant. But I'm changing the capacitance by doubling the area of the plate. So I'm increasing the capacitance by a factor of 2. That means that the voltage has to go down by a factor of 2. So it was 200 volts, and now it's going to be 100 volts. So number 12 is C. Consider the circuit. What is the voltage across C3? Okay, well, they all have the same capacitance. So this is C, and this is going to be 2C, because I add these up. C2 plus C3 is 2C. Remember, Q is equal to CV. So the bigger capacitor has the smaller voltage. So I have 12 volts here. That means I'm going to have 4 volts here and 8 volts here. These numbers have to add up to equal 12. This number has to be half of this number because of this relationship. So 8 and 4 are the only ones that fill that bill. So number 13 should be 4, which is D. Number 13 is D. What is the equivalent capacitance of this circuit? All right, we have to begin here first. 1 over 1 over 3 plus 1 over 6. That's 1 over 2, 6 plus 1, 6. That's 1 over 3, 6, which is equal to 2. And then we say this capacitor, which is now 2 microfarads, plus this one and plus this one, that's 2 plus 1 plus 2, which is equal to 5 microfarads. So number 14 is D. And then what is the charge on C1? So where am I here? Get rid of some of this stuff. I want to know what is the charge on this capacitor. Well, as a similar question as I had before, I know that I have 12 volts across here. So this is the same setup as I had. Well, it's not exactly the same. It's sort of the same. I have 12 volts there. Then I know the smaller capacitor, which is half the bigger capacitor, has to have 8 volts, and this has to have 4 volts. All right, so if I'm looking for the charge, I know I have 24 microcoulombs there. That's 8 times 3. So number 15 is B, but let me show you a different way of doing that. Number 15, let me erase some of this stuff. There's a little space here. Actually, let's do it up here. So I'm going to take this circuit, I'm just going to draw the battery, and this branch up here, that's a 3 and a 6. So I have a 12 volt battery, and a 3 microfarad and a 6 microfarad. The equivalent of those is going to be 2 microfarads. And I notice I've just drawn that one branch, but in parallel they all act independently. So I can isolate them in this way and deal with them independently as well. Still have 12 volts here. Now, I can find the charge on this capacitor. Q is CV. That's going to be 24 microcoulombs. And capacitors in series all have the same charge. So each of these, the 3 and the 6 microfarad capacitor, are going to have 24 microcoulombs. And then you can go back and then find out, since I know they each have 24 microcoulombs, I can find the voltage, which is Q over C, and I'll get the result that we had before. 24 over 3 is 8 volts, and 24 over 6 is 4 volts. So it's a different way of getting the answer, but it's a little more circuitous. Parallel plate capacitor is an area separation. The charge is 4 microcoulombs. What is the potential difference? All right, well, first, so I want to know V, which is Q over C. I'm given the charge, so I need to find C. That's epsilon naught A over D. There's no dielectric here, so that's 8.85 times 10 to the minus 12. The area is given 0.2 divided by the distance 0.0001 meters. So that gives me a capacitance of 1.8 times 10 to the minus 8 farads. And then if I have 4 microcoulombs, this is what, 100, or no, it's 0.00, well, I'll just keep it in 0.0018 microfarads. But look, I'm just going to keep everything in SI units. I think that might be easier for you. So this is going to be 4 times 10 to the minus 6 coulombs. Here you have to be careful with your units. 1.8 times 10 to the minus 8 farads. And I get 222. But keeping proper sig figs is going to be just 200 volts. So number 16 is B. Now again, another way you could have done this is we could have said, well, 4 microcoulombs divided by 0.0018 microfarads. If I've done my units correctly, that should work out. Let me just double check. I did not do it correctly. Let's see. So, no, this should just be 0.018, pardon me, 0.018 microfarads. So this would be just 0.018, and then that also gives you 222. Either way, I would probably do it this way, where I convert everything to SI units, because I think that's probably easier. Let Q denote charge, V denote potential difference, and U denote stored energy. Of these quantities, capacitors in parallel must have the same what? Well, we know capacitors in parallel have the same voltage, right? but they don't necessarily have the same charge, and they don't necessarily have the same energy unless the capacitors are all the same, but not necessarily are the same. So V is the only one. E is 17. Two capacitors with CA greater than CB and are connected in series with the battery, which is following is true. Okay, well, so I have two capacitors in series. CA, let's just give it some values. We'll say this is 8 microfarads, and CB is 4 microfarads. All right, I know that the charge is the same. Let's look at the others. There's more charge stored on CB. That can't be true because they're in series, they have the same charge. There's the same charge stored on each capacitor. Right, that's a true statement. Let's look at the others. There's the same potential difference across the capacitors. That is not true. There's more charge. No, that's not true. So B is the right answer for number 18. That goes back to our basic rules. All right, entering into chapter 3 portion. Current has units of coulombs per second. It's an amp, but an amp is 1 coulomb per second. What is the current through this resistor? Okay, I is V over R. It's 12 volts over 3 ohms. 4 amps. Conventional direction of current in the previous question would be what? Okay, well, it comes off the positive side of the battery and goes in this direction. That is clockwise for 21. Which of these has a greater resistance? All right, the one with the lower power has the greater resistance. So it's going to be the 60-watt bulb. You can think about this in a couple of different ways. P is V squared over R. And the one with the greater resistance gives the lesser power. I know this, the voltage here remains constant. Or as we talked about in class, you can intuit it. You can say, well, the one with the greater resistance resists the flow of electricity more. So fewer electrons flow, and so you get less power, so you get less brightness, which is the 60-watt bulb, or the heater, for that matter. Current is a measure of which of these? It's not the speed, and it's not the force, it's not the energy, it's the amount of charge. Remember, we're looking at the amount of charge over seconds. And it's not the resistance, so it must be D for number 23. If the potential difference across the resistor is doubled, which of these happens? Well, V is IR. If I double the potential difference, it's going to double the current. So the current is doubled, the current is not halved. The resistance isn't affected. The resistance, okay, so A is the only answer. 24 is A. So these wires, wire is 4 times the area and twice the length. How do their resistances compare? Well, first of all, just looking at it, I can tell that the resistance of wire A is going to be less than the resistance of wire B because it's a bigger, actually, no, I don't know that right off. So let's, I know that resistance is rho L over A. And the resistance of wire A, let's see, wire A is twice the length and 4 times the area. All right, so that gives me a factor of 1/2. So the resistance of wire A is half that of wire B. That's going to be C. The resistance of wire A is half that of wire B. A wire carries a steady current of 0.1 amps over a period of 20 seconds. What total charge passes through the wire in this time interval? So Q is IT. That's the definition of current. That's 0.1 times 20. It's going to be 2 coulombs. And 27, for a certain diode, the current flows unimpeded in one direction. For current in the opposite direction, what is it? Well, remember, a diode opposes the flow of current in one direction, so the resistance goes very, very large. So B is the right answer for number 27. And we did a plot here where we had plus or minus I, plus I, minus I, and then the resistance. Resistance is very low for current in one direction, and then in the other direction it goes very high. So that's how a diode works, or that's what it does actually. Here's all the answers.